One of my favorite math concepts across all of mathematics really is e to the x, where e is some constant 2.71828, yada, 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 right? It's an irrational number, right? So I can't list the entire value out. But e to the x is used for a lot of things, a lot of real life applications, right? It's used in finance, it's used in modeling populations, both exponential and logistic, right? It's also used in complex math. It's used a lot in complex math, right? So your hyperbolic trig functions, sine h, cos h, tan h. You also have your Fourier transform, your Laplace transform, whatnot. Right? They all use some variation of e to the x. But why am I glazing e to the x so much, and what makes it so special in the first place, right? So the derivative of e to the x is e to the x. That's it. That's it, all there is to this video, right? So e to the x, if I were to, this is a graph of e to the x, by the way. If I were to put some point here, e to the c, right? So this is some distance c. If I were to draw a tangent line to this, damn, that was actually pretty close. If I were to draw a tangent line to this, the slope of this, your change in y, and over your change in x is going to be e to the c. Fascinating, right? One other thing I'd like to mention, right? So the derivative of e to some constant c times x is going to be c e to the cx. You'll learn more about this in chain rule, right? But if I were to look at this visually, you could see that it's you have some constant that is compressing your function horizontally, right? You would need a larger vertical increase or vertical stretch factor in order to compensate for that, which is why this c kind of hops down, you could say. It's also used in modeling populations. So let's take a look at the differential equation for a constant growth rate. So some k constant, some k scalar, right? If you were to solve this, you'll get to this much later, but this would come out to the form c times e to the kt, right? So you're using e to some exponent kt, right? Oh, I forgot to write this. So this would be like dt. I mean, the variable there doesn't really matter too much, right? But this general form is used a lot when it comes to modeling populations exponentially. Likewise, the derivative of the natural log of x is also quite interesting. Being the inverse of e to the x, the natural log of x, the derivative of the natural log of x is equal to 1 over x, which corresponds to a graph something like that, right? Not drawn to scale, of course, but right, it's just for visual representation. If I were to choose maybe, I don't know, this point on 1 over x, right? This would correspond to a tangent line of something like this, right? Considering the value of 1 over x is positive and pretty large, right? The slope of the tangent line at this point is also positive and also quite steep. In contrast, if I were to choose maybe this point here on the natural log of x with a tangent line of something like this, right? Still positive, but much less steep, right? It would also result in a value on 1 over x that is still positive, but not very large, right? One other thing I should mention is that while the domain of 1 over x extends for all values aside from x is equal to 0, right? The function, the natural log of x, is only valid for values greater than 0, right? So as a result, the derivative of the natural log of x will only take on values, or will only be defined for values greater than 0. You're going to have to restrict the domain to be x is greater than 0.